So, today we will be talking about theory of column. Now, first of all, we must define what is column. Column is geometrically looking like a beam. So, one of its dimension is quite long compared to the other dimensions. So, the length is a predominant dimension here compared to breadth and width. That is more or less like a beam if we think in terms of geometry. Now, the basic difference of column with beam is the loading. In beam, loads acts perpendicular to the axis of the member, but for column, load acts along the axis of the member. Number one. Number two, we are much more interested if the load is compressive in nature. So, first of all, load should be along the axis and it should be compressive in nature. Now, column, or rather the theory of column, it is divided into two groups. So, one group we say it is a short column, another group we say it is a long column. Right. So, we can say case 1 it is short, number 2 it is basically the behavior of this short column and long column is entirely different. So, our primary concern is with the long column, how it will behave under the action of compressive force. But before that we can discuss something on short column, then switch over to the problem of long column. Now, for short column and long column, the primary difference is the ratio between the length and its lateral dimension. So, say B, D, if it is a rectangular section, there will be width, there should be a thickness, and there should be a length. So, the ratio between the length and the other two, that will give the guideline whether the column is a short column or long column. Right. Say if we take a say this pen, it is a cross sectional area. So, if we take that length, the phenomena will be something like that, and if we cut a single small piece from here, so the cross sectional area is same, but the length is rather small, or we could take a much longer stick having a same cross section. So, structural behavior of a small piece and a long piece will be entirely different. So, the ratio of the length compared to the lateral dimension, that will give the guideline whether the structural component can be handled as a short column or a long column. Now, if we start with short column, say we can take a problem like this. Say there is a piece of column, length is not very big, definitely it is a short column. Say it is resting here. Now, if we apply a load at its center, or rather the centroid of the cross section of the column, at any station your stress distribution will be something like this. It will be P by A. Say P is the force and A is the cross section. So, that part the stress sigma will be P by A. Right. Now, if the application of load is be different, say same problem if we pick up, say that is the center line. Now, load is acting not at the center, say it is acting little bit away from the center. So, same P and say the distance from the centroid of the load, if we say it is E. E sometimes we define as eccentricity, right. So, eccentricity, right. So, if the load is a little eccentric, not exactly on the centroid of the cross section. Now, the cross section may be a rectangular cross section, it may be a circular cross section, it may be some elliptical cross section or any arbitrary cross section. Say if we take a section, what will be happening? Say we will get, say if I draw the section here, there might be a section like this also. So, just arbitrarily I have drawn. Main idea is this part should be symmetrical about this. Now, so this will be the centroid and the load may be acting not at that point, it is acting at some other point. So, the distance between these two we say it is the eccentricity, right. Now, if the load P is acting like this, the load P we can shift at the centroid, but we have to take a moment, right. Now, say there is a load P, say on a structure it is acting. Now, if we take a force like this, so if it is P, this is also P. So, initially it is P. Now, this part we can just add. So, it is just like we add something, subtract something. So, this set of force is not going to affect the structural deformation. So, it will be identical. Now, next step we can take this load and these two load we can take separately. This P and that P, they will form a moment couple, right, and force wise they will cancel each other. So, that problem we can think in that manner, say this is the structure, the load is there plus there is a moment. So, moment is equal to P into E if the distance is E and this is the P. So, the force here P is not acting at centroid, it is little bit away from the centroid at a distance of E. So, we can shift the load at the centroid, but along with the force there should be a moment that will be P into E, right. So, this problem we can just think in that manner. This is the column. So, the equivalent force here is the load plus a moment. So, this is basically your force P and this is P into E. Now, the effect of P, you know, P acts at the centroid, there will be a uniform distribution of stress and that will be P by A, and there is a moment that is P into E. So, if we apply a moment here, we know it will generate a bending stress, and bending stress at the neutral level it will be 0 and it will vary in a linear manner, right. So, if we take the problem in this manner, the stress block became little erratic. If we put it in a correct way, it should be like this. Right. Or if we just draw the final form, so the load, actual load is P here. So that distance we have defined as E. That with the load we have shifted at the centroid is P into the moment PE. So that part we can just add in a separate way. So there is a load here P that will give the stress distribution. So that part already we have defined. It will be your sigma equal to P by A, and here if you apply moment P into E, so it will be a just bending problem. So there will be a bending stress. So this part will be your maximum bending stresses, right. So this part will be your M Y by I. So if it is this side is, say it is C1, this is C2, it will be C1, this will be MC2 divided by I, right. So it is a C1, this is C2, so it will be MC1 by I, MC2 by I. Now if we add that, this stress will be how much?
Two perpendicular.
There is a stress MC1 by I, there is a stress P by A. So both will add together, and here this stress will be this minus this, it will be P by A minus MC2 by I, right, this small value. So due to the direct load, there should be a direct compression uniform, and due to the bending, it will be also the normal stress, one will be plus, another will be minus. So this side it will be compression, this side will be tension, here it will be entirely compression. So this part and this part will be added together, and this part and this part, because this part will be deducted from this side, right. So here the stress block finally whatever you will get here. So if I draw that block again from this side, so that is the P. So the stress block whatever we are getting here, this part you can say it is sigma max, it will be P by A MC1 by I, and this part if we say sigma minimum, so sigma minimum will be P by A minus MC2 by I. Right. Say if you take that member, apply a moment, so this fiber will be in tension, that fiber will be in compression, and if you apply direct load, all the fiber will be in compression. So, this side it will be compressive additive, this part will be compressive minus that part you are getting in a form of tensile stress due to the moment. So, it is very simple. Say you are standing straight. So, you try to think about the pressure on your foot, right? So, it will be uniform. If you try to just slightly bend.
So, it is possible that at one particular part there will be no compressive stress also.
Yeah, so that part I will come little later. So, if you just try to bend little forward, so here you will get more pressure because you have a tendency to bend that side, means the load is on the forward side, means there is a movement in the forward direction. So, that side you are getting more pressure, whereas your heel part you will get less pressure and sometimes your heel may lose contact. What you are talking about, there will be no stress there, compressive stress, right. Now, here it will not be no pressure, some pressure will be there in a negative form, that will be your tensile stress, not a compressive stress. Now, here in bending MC1 by I and MC2 by I, they are the bending stresses, maximum one is compressive, another is tensile, and here P by A, that is the direct compressive stress. Now, if it depends on the magnitude entirely, so this side there is no doubt it will be always compressive force, but here if P by A is more, say P by A is 10 and MC2 by I equal to 5, then it will be still compressive, but value will be 10 minus 5 will be 5. But if this is 10 and if it is say 15, right. So, bending part is more compared to direct mode. So, this negative part will be more. So, 10 minus 15 it will be minus. So, minus 5 compressive stress means there will be a tensile stress of 5. Okay. Now, there are some situation we do not allow this tension to be developed. In some cases there is no problem, it may be tensile, it may be compressive, but there are some cases, say particularly I was giving the example of pressure below our foot. Now, if we try to design some foundation of some structure of some machinery, now say it is resting on something, some concrete block or somewhere. Now, the if eccentricity is more, so here there is no contact. So, it can take direct compression, it can't take tension, right. When it is a continuous one, it can take tension as well as compression, but here only that pressure it can take. So, the tensile stress it can't take. So, definitely if there is some foundation, so this part there will be no tensile. So, automatically their stress entire pressure will be 0 and stress block will be entirely different. That part sometimes we try to avoid, or there might be some other type of example where this part we try to make is at least 0 or a small positive value. So, definitely C1 C2 I is the property of that cross section. So, M is P into E. So, E is a controlling factor. So, if E is very very high, if you go on increasing E, moment part will be go on increasing and this part will be more, and automatically it will switch over to 0 and the other side, negative side. So, there should be some restriction of this E eccentricity. Beyond that, if we go, then that problem will occur, means
it could reach a position where P upon A is equal to MC2 upon I.
Yeah. So, that is the limit. So, that should be the limit. If it is that critical point, then the H your stress will be equal to 0, or this particular stress will be equal to 0, right. Now, let us consider a rectangular cross section and try to investigate how long we can go working. So, what should be the maximum limit of E. Now, you have rather uttered the solution that sigma minimum it should be equal to 0, and we have to put the appropriate value of I and C2. Now, if the cross section is a rectangular section, say this is your B and that is say your D, right. So, that is the centroidal level, say E is somewhere here. Okay. Now, if we take sigma minimum, so sigma minimum will be B by A is how much? It will be B into D, and this one will be M. What will be C2? C2 will be B by 2, and I will be your
BD squared upon 12.
bending will be along this direction, so it will be BQ.
B cubed B upon 12.
So, but axis we are taking D is on top.
We are taking moment. If we put the force here, there will be a moment, right. So, you try to think there is a column and it will try to bend. So, bending about this axis. So, it will be dBq. We could take B this one, D that way, anyway, the way we have taken it, it will be dBq divided by 12. So, this should be and that should be multiplied by E, right. So, M into E is the moment, C2 is B and B by 2 and I is B dq by 12, right. Now, that will be the minimum value. Now, if we take it is a limiting case, say this stress is equal to 0, means this stress should be equal to this stress, equal and opposite. Now, here if we simplify, it was M, we have written M as well as E. So, it will be P into E or M, rather E part we just eliminate from here, next time we will put it. So, this B one part will cancel, here D will be there. So, we can write say P divided by BD minus say PE, at this level we put B, and here it will be 6, and this part we can make say D B square equal to 0.
So, C1 we are taking as B by 2.
B by 2, because we are calculating stress here, right. So, this is C1, this is C2, both are is equal to your B by 2, B by 2, rather we could take D and B this side. So, I have given BD in such a form, okay. So, it is creating little confusion anyway, okay. So, BD here it is 6, so 6 it is placed here at the top, B will cancel 1B, it will be B square, D is there. So, BD part also we can cancel and P we can cancel. So, from here we will get E equal to
1 by 6.
E will get you will get
B by 6.
B by 6, right. So, E will be your B by 6 maximum. So, this side it can B by 6, and in a similar manner it can go here, right. So, that is the range. So, it can go up to here. So, you can say there should be a limit b by 6, right, or we can write E should be less than equal to b by 6. So, eccentricity, if it is within minus b by 6 to plus b by 6, the entire cross section, it will be compressive stress. There is no chance of occurring any tensile stress, right. So, it should be less than or equal to. So, if it is equal to the extreme end, it will be 0. If it is less, some value will be there, compressive stress. So, that problem if we put in the reverse manner. So, B if it is in a minus side, so if it is B by minus B by 6, here stress will be 0 and from there it will generate. So, there it will be a triangular stress. If it is here B by 6, it will be a triangular stress. If it is less than that, it will be some value, it will be a trapezoidal type of stress block. Right. Now, eccentricity we have made along B, it may be along D, it may be acting somewhere here. So, same thing it will be valid. So, it will be at d by 6 or minus d by 6. Now, if it is here, what will be happening? Simultaneously eccentricity will be there along x axis, along y axis, right. So, first we have taken eccentricity along x axis. Now, same logic will work if eccentricity is along y axis, only the directions we have to change. Now, it may be here again, not diagonal. It may not follow 45 degree or a line joining corner to corner, any arbitrary, say if it is 1 millimeter, it may be 5 millimeter there in the other side. So, their eccentricity will be in both the direction. Now, such a problem can be handled in that manner. Say if I take any cross section. So, any cross section is quite important here, I will discuss little later. Say this is the centroid or a cross section of a column. Now, if the load is acting here, say this distance we can define as Ex and that distance we can write as Ey, right. Say that side if we write x and this side if we write y. So, along x the eccentricity we are defining as, say this is the load point. So, this is Ex and this is your Ey, right. So, this load we can shift here. So, it will come here with a moment P into Ex about y axis. Now, next step, if you shift that load, there will be a moment along x axis P into Ey, right. So, what will be happening? So, if we shift here, ultimately at the centroid, so we will get P and there will be a moment about x and there will be a moment about y, right. Now, this mx means moment about x. Sometimes we can take moment about x or we can say moment about x along x. So, about is the direction of the vector and it will try to give a bending along x, sometimes we say along. So, anything we can follow along or about, right. So, if we take along, at least this Ex part it will be followed. Okay. So, we can say P into Ex and it will be P into Ey, right. So, here if we shift from here to here, so it will be P into X, that moment will be moment along x or moment about y. So, you can say it is moment along x or about y, whatever you can define. Similarly, this is moment along y or about x, right. So, once you will bring it here, next step if you go there, there will be moment about x or moment along y. So, this part is P into Ey. So, there are two moments. So, there is a moment along this, there is a moment along that, plus there is a force. So, it is just like this, the force was here, we have shifted there, there is a moment along this, there is a moment along that. So, it is a biaxial moment, right. It is mx my plus p. So, p will contribute straight away p by a, and mx and my, that will generate my by I. So, sometimes I have to take along this, sometimes you have to take about the other direction, because moment will be along this or along that. So, we can write stress at any point. So, stress will be P by A. So, that will be the direct stress, and your mx will be your P into Ex is mx. So, here it will be that into x by Iy, right, or Iyy we can say. P into Ex, that is mx, mx is along this. So, if we give a moment, so at any distance, so mx by Iyy plus your P into Ey, so moment about this. So, at any point y, it will be I xx. This along about x y, that we can change little bit. Okay. So, there is no unique relation that we have to take in that manner. Okay. So, what will be happening? There should be a uniform level of stress due to P by A and P E x x I y y. So, here there will be a variation of stress along x. So, P E x I y y, they are constant quantity, only the variable quantity is x. So, along x there will be a variation. So, you can say there is a stress block having a top surface like this, inclined along x, and here it is P u y y by I x x. So, there will be a variation like this, right. But here due to that moment, this side will be the compression and this side will be tension, and due to the moment this side, here it will be compression, other side it will be tension. So, in the positive direction of y it will be plus, positive direction of x it will be plus, on the negative direction of x it will be tension, means minus, on the negative side of the y it will be tension or compression due to the bending. So, that will be the a total expression. Now, this part we can express in this form, this P by A we can take common, P divided by A right. So, it will be 1, and here this P we are taking common. So, there will be, it will be A and E x, it will be there. So, this part sometimes we write that there is a term called radius of gyration, right. So, the definition of radius of gyration is, so it is written as r and it is square root of I by a. And normally I, the unit is say meter to the power 4 and area is meter square. So, ratio will be meter square. So, r will be in the form of meter. So, it is called a radius of gyration. Now, here we can say A above. So, I y by a if we put. So, this part will be r square, right. So, we can write E x by r square. So, this part we can write as y, right, and this part we can write E y divided by r x square. So, this r y and r x we have defined because about y we are calculating I. So, it was defined in that manner. Now, that is the general expression. Now, if we have the if we want to express the stress at the extreme fiber, so this x we can write say C1x, this is a C1y, other end it is C2x or C2y, right. So, for some specific case we can write the extreme values. Now, here we can take the example of a rectangular section and try to see what is happening. So, sigma equal to P by A 1 plus E x x by r y square E y y y.
This is the maximum stress.
This is the stress at any point. So, it is x y. Now, let us take one rectangular section. It will be say this is x and this side is y, right. That is B and this is D. Now, we repeat that expression, it is P by A 1 plus your E x x by r y square E y y by r x square, right. Say the load is acting somewhere here. So, this is your E x, this is E y, whatever we have defined, and stress at any point will be something like this. Now, we are interested for the limit of E x and E y. Okay. Now, earlier we have seen if the load is at b by 6, so here the limiting line was passing along the outside line, and if it was here, it was along this line. Now if it is here, it will be somewhere some line, there it will be 0. If the load is acting here, say at b by 6, then your 0 stress line will be here. If it is beyond that, it will be inside. Now if we take this side is d by 6, so 0 line will be here. If it is more than that, it will be here. After that, tension will be generating. Now if it is here, so the 0 line will be along this, right, because there is a moment in that direction, resultant moment. So there will be some line that will have a 0 stress. Beyond that, it will be tensile stress, and this side it will be compressive stress, right. Now so we can, this Ex, Ey, anything if we pick up, there should be some line. So this side will be compression and that side will be tension, and there should be a limiting line. Now if we don't allow the tension within that section, the line should pass along this. That will be the extreme, right. So if we are interested that everywhere it should be compression, so there will be no tension. So this line will not allow to enter inside. So if you give high value of Ex and Ey, definitely tensile stress will be generated, and there should be some line beyond that, it will be there, right. Or we can say this sigma, this line is basically the 0 line. So if that is 0, Ex, Ey, say Ry, Rx, these are the section properties, right. Or we can write your Exx by Ry square plus Uyy by Rx square plus 1, that should be equal to 0, right. So that critical point, if sigma equal to 0, then this part should be equal to 0. So what is that? That will give the equation of that line, right. Now say there is a Ex and there is a Uy, and for the section Rx, Ry are known, and due to that situation we are getting the general expression of sigma is this. Now on that section, say there will be some point where sigma will be equal to 0. So if we equate 0, then this part will be equal to 0, right. We can understand if the load is here, there should be a line, along the line it will be 0. If the load here, there should be a line, along that it will be 0. If it is like this, there should be some line like this, and on that line the stress should be 0. Now the stress, if we make 0, that should be equal to 0, or rather this will give the equation of this line.
It will be diametrically through the center, through the central axis of the
It not necessarily it should be diametrically on that line. It depends, whatever will be the Ex and Ey value.
but directly opposite the central.
We can say it is say this part if you bring it down, so x by Ry square by Ex, y by rx square by ui, right, that should be equal to minus 1. So any straight line, if we have a equation, say x by a plus y by b equal to 1, what is that line? So this is x by a, this is y by b, that is equal to 1. Now here x by this quantity, y by this quantity is equal to minus 1, or if you make it that is plus 1, means it will be minus minus some line, okay. So if it is xy, this is minus, right. So there will be some line. So x intersect is this quantity minus, y intersect is this quantity minus, y is this way positive. So both will be minus minus, that will be equal to 1. So it will give basically the equation of that curve, and what will be the value of this one or this one, that we can get from this equation, right. Now we want that line should not be here or here, it should be on the edge, right, so that entire section it should be equal to it will be compression, no tension. Now in that case, what will be the xy coordinate? So this line, so there is a point xy on that line, that will be minus b and minus d. So we can put here ex b by 2 minus ry square minus ui d by 2 rx square plus 1 equal to 0. Now from here we will try to get the value of the eccentricity ex and ey. Says sigma general expression we have written. Now if we make sigma equal to 0, then we are getting this is equal to 0. So that will give the equation of that line. Now that line, if we want to keep outside the column section, the extreme point is here. So on that line there is a point and it has a coordinate x equal to minus b by 2, y equal to minus d by 2. So that part we have substituted, that extreme case. Now if it is there, from here we will try to get the equation of ex and ey. So this is ex, this is ey. Now this ex and ey, this ry and rx we can generate. So what is rx and what is ry? It is square root of that I and all those. So those values we will substitute here, and finally we will get the expression of ex and ey and try to get the limit. So you we can keep up to this level. Next class we will continue the remaining.
(1951). A young nation aspiring to find ways to fulfill a dream lays the foundation of an institution that will give aspiring technocrats the license to fly high. The first Indian Institute of Technology is born at Kharagpur. Founded on the basis of the recommendations of the NR Sarkar Committee that was set up in 1945 to consider the development of higher technical institutions in India, The institute was first established in 5 Esplanade East, Kolkata, before it moved to Kharagpur in 1951. With Sir Gyan Chandra Ghosh as the first director and Dr. B.C. Roy as one of its founding guardians, the institute established itself as the symbol of a young, dynamic and resurgent nation. As top students rubbed shoulders with the most celebrated of professors and scholars, visions took shape. And IIT Kharagpur continued to play the pioneering role that was envisaged for it, enabling India to become a knowledge powerhouse that it is today. So, no matter which walk of life they choose, the IIT KGPite stands tall. And so does the institution that bred him, in majestic splendor. The alumni of this institute command global respect. Their distinguished presence at the helm of global giants is a matter of national pride. For the students of IIT Kharagpur, it is impossible to erase any scratch of memory about their alma mater. In fact, some come back to invest sentiment, pride, and money, to see the institute they call home rise to even greater heights, structurally, functionally, as well as holistically. Their singular aim is to make IIT Kharagpur an institute, whichever way you look at it, par excellence. A man's journey into quiet accomplishment and the Hall of Fame starts with the right step. And the training and placement cell of IIT has been the efficient facilitator in this regard for over 30,000 graduates. Having placed more than 95% of its students in a wide range of industries consistently for over 2 decades, it is no wonder that the institute is the most preferred campus for technical recruitment of quality manpower. With infrastructure like industrial power and communication facilities, in addition to its excellent research and consultancy facilities, STEP, or Science and Technology Entrepreneurs Park, aims to assist the budding entrepreneur into a successful adventure capitalist, guiding him right from the concept, institutional financing, production, leading up to the launch and marketing of the product. With its rich pool of talent and excellent infrastructure, it is no surprise that through the last 3 decades, IIT Kharagpur has developed strong liaison with the industry. SRIC, or Sponsored Research and Industrial Consultancy Cell, was formalized as the Special Industry Interaction Cell in 1982. Devoted full-time to handle industrial projects and consultancies, and for deploying and propagating intellectual property. Successful sponsored research projects straddle a wide spectrum, ranging from computers, communication and biotechnology to robotics, photonics, and food processing. The setting up of a state-of-the-art VLSI CAD laboratory and tie-ups with GE in areas ranging from vehicle structure design to electrical communication and software technologies are excellent examples of IIT Kharagpur's ever-evolving pioneering spirit. Collaborations with a host of national and industrial majors are a testimony of its proven expertise and research repertoire.
आकाशादि हार मिलेছে লোকে মোরা যাবো তাই দেশের তারে খাচ্ছি সবে আমাদের গর্ব ভাই যোগ কর্ম সুকৌশলম योग कर्म सुकौशलम नैके क्षेत्रे वर्ण योगः कर्म सुकौशलम आदर्शाय मादर्शाय प्राणदास्मह्वयम् योग कर्म सुकौशलम योग कर्म सुकौशलम योग कर्म सुकौशलम.
Indeed, in this golden jubilee year, as the celebration continues, Pandit Nehru would surely have been a proud man today. For him, IIT Kharagpur was always more than just an institute of technology. In his own immortal words, it is indeed a fine monument of modern India.